Hi, this is Dr. Goldstein, and today I'll be discussing compositions and derivatives of inverse trigonometric functions. So let's begin with the question, what is sine of arccosine of x? So this is a composition of a trigonometric function with an inverse trigonometric functions, and these compositions tend to simplify very nicely. So let's see how that works, and to begin, let's look at this inside expression, arccosine of x. So recall that the domain of arccosine of x is just from -1 to 1, so everything that we're doing here only holds for values of x that are between -1 and 1. So recall the definition of arccosine. Arccosine of x is some theta where cosine of theta is equal to x and theta is between 0 and pi. Well, what we know about cosine is that cosine is equal to adjacent over hypotenuse. And so if that is equal to x, we can write x as x over 1. And so we can draw a right triangle. And we know that theta has to be between 0 and pi, so this is a reasonable picture for theta. We can draw a right triangle that has the angle theta in it, and then because cosine of theta has to be x over 1, we know that the adjacent side in this triangle has to be x, and the hypotenuse of this triangle has to be 1. And now what we know about this third side of the triangle is the Pythagorean theorem. So we know that x squared plus this third side b squared has to be equal to 1. So b squared is 1 minus x squared, and b has to be technically either plus or minus the square root of 1 minus x squared. But in this case, we're talking about the length of a side of a triangle, and we know that our angle is between 0 and pi, so we know that this vertical length is actually positive. So we know that b has to be the positive square root of 1 minus x squared. Okay, now this is fantastic, but what on earth does it have to do with our original question of sine of arccosine of x? Well, remember, arccosine of x is this angle theta that is now in this triangle. And what we know of sine of an angle is that it is opposite over hypotenuse. And we computed that the opposite side for that angle has to be the square root of 1 minus x squared. That was our b. And we know that the hypotenuse of that triangle was 1. So what we've just seen is that sine of arccosine of x, for values of x between -1 and 1, it's always equal to the square root of 1 minus x squared. So let's look at this statement in a little bit more depth. So this is what we just said. For x between -1 and 1, sine of arccosine of x is equal to the square root of 1 minus x squared. So the first thing that we can note is that both sides of this have the same domain. In both sides of this equation, the only values of x that you can plug in are between -1 and 1. We know this for sine of arccosine because those are the only values that arccosine is defined for. And then for 1 minus x squared, if x is bigger than 1, we end up with a negative inside of the square root, and that doesn't work. Another reason why this makes sense is because if we look at the top half of the unit circle, we know that arccosine of x is always going to be between 0 and pi. So the angle theta that we found in our work on the previous slide is always going to be between 0 and theta, so we're always looking at the top half of the unit circle. And so values of sine on the top half of the unit circle are always going to be positive. So it makes sense that sine of cosine of x is always greater than or equal to 0. And also, if we're taking square roots of things, well, square roots are always greater than or equal to 0. And so, again, this just makes sense because those two line up. I know that sine of this arc cosine is always going to be greater than or equal to 0, and I know that the square root of 1 minus x squared is also going to be greater than or equal to 0. Okay, let's see one explicit example of this to really believe that this is true. So let's look at when x is equal to the value minus 1/2. So on the one hand, if we use this formula that we have at the top of the slide, I know that sine of arc cosine of minus 1/2 is going to be the square root of 1 minus negative 1/2 squared. So this is the square root of 1 minus 1/4, which is the square root of 3/4, and I can simplify this as root 3 over root 4, and so this is the square root of 3 divided by 2. So that's what I get using the formula on the top of the page. Alternatively, I could compute arc cosine of negative 1/2 explicitly, and so I know that this is going to be equal to some value theta, where cosine of theta is equal to negative 1/2, and theta is between 0 and pi. So if I look in the unit circle, where cosine could be equal to negative 1/2, so here's negative 1/2, and so I know that I would have to intersect the unit circle here. And then if I think about what the side lengths of this triangle have to be, if this side is 1/2, then this is a 30, 60, 90 triangle. The hypotenuse is always 1 on the unit circle, and so the opposite side has to be root 3 over 2. So this angle in this triangle is pi over 3, and so my angle theta that I'm looking for is 2 pi over 3. And so I know that arc cosine of negative 1/2 is equal to 2 pi over 3. So again, I know that because cosine of 2 pi over 3 is negative 1/2. That's what we found using the unit circle. And I also know that this value, 2 pi over 3, is between 0 and pi. Okay, so now if I want to compute sine of arc cosine of negative 1/2, I've explicitly computed arc cosine of negative 1/2. So this is sine of 2 pi over 3 is the same as sine of arc cosine of negative 1/2. And then if I want to calculate sine of 2 pi over 3, I'm looking for the length of the vertical side of this triangle on the unit circle. I can use my work from before. So this is going to be equal to root 3 over 2, again, from the unit circle picture. From this length right here. That's what we're using. And notice that these match up. When we use the formula that was on the top of the slide, we got root 3 over 2. And when we compute this explicitly by evaluating arc cosine and then evaluating sine, we also get root 3 over 2, which we should because we're saying that these two things are equal. Okay, so now hopefully you're convinced that sine of arc cosine is the square root of 1 minus x squared. Now, at the beginning of this video, I said that we were going to talk about compositions and derivatives of inverse trig functions. So we're going to use what we just did to calculate the derivative of arc cosine. Now, before I actually do that, I'm going to talk about something that I see people do a lot if they're not familiar with this. If you're trying to take the derivative of arc cosine of x, you cannot take down this minus 1 power, subtract 1 from it, and then take the derivative of cosine as if this was a chain rule problem. This is not a chain rule problem. Because that's not what arc cosine means. Remember, arc cosine is an inverse function. A better notation for remembering this is this actually writing out arc cosine rather than writing this as the exponent minus 1. So just to remember that this is an inverse function, that minus 1 really does not mean, it does not mean that we have an exponent of negative 1. Okay, so in order to calculate the derivative of arc cosine, we know that cosine of arc cosine is equal to x. So this is for values of x that are between minus 1 and 1, because those are the only numbers that we can plug into arc cosine. And here, we're just using the definition of inverse functions. Whenever you have a function and its inverse, when you compose one inside the other, they cancel each other out. So whatever you put in is the same as what you get out. So this is our starting point, and now we're going to take the derivative of both sides of this equation. And on the right-hand side of this equation, this is very easy. The derivative of x is just 1. And on the left-hand side of this equation, I know what the derivative of cosine is. I know what the derivative of the outside is. And so I can use the chain rule to take the derivative. And I get the derivative of cosine is negative sine. I always just plug the inside in unchanged. And then using the chain rule, I would have to multiply this by the derivative of arc cosine. So again, in this step, I'm just using the chain rule on the left-hand side. Now, what we want to find is this. We want to find the derivative of arc cosine. This is our goal in this problem, and so we're going to solve for it. We're going to solve for that expression. We're going to divide both sides by negative sine of arc cosine. And this is why at the beginning of this video we computed sine of arc cosine. We computed already that sine of arc cosine of x is equal to the square root of 1 minus x squared. And so what we get when we plug that in is we have this negative sign from before, and we have 1 over the square root of 1 minus x squared. And so that is the derivative of arc cosine. To summarize, we computed the derivative of arc cosine, and in a very similar way, you can also compute the derivative of arc sine, and that is 1 over 1 minus x squared. And you can compute the derivative of arc tangent, which is 1 over 1 plus x squared. Now notice, for both arc sine and arc cosine, the domain of both sides is just x equals minus 1 to 1. And notice for arc tangent, the domain of both sides is from minus infinity to infinity.